At a classified Air Force installation in Missouri, a $2 billion aircraft sits in a climate-controlled hangar while a team of technicians works through a checklist that runs to several thousand individual steps. Not several hundred, several thousand. Miss any one of them and the most expensive, most capable stealth bomber ever built becomes an extraordinarily expensive piece of wreckage. The B-2 Spirit is the aircraft that ends conversations about air defense. Its ability to reach any target on Earth, penetrate any air defense system currently in operation, and deliver precision munitions without detection has defined American strategic air power for 3 decades. But the capability that makes headlines is only possible because of an obsessive, exhausting, and largely invisible maintenance process that happens before every single mission. This is what that process actually looks like. From the first torque, wrench turn in the weapons assembly building to the moment a 2,000-pound bomb makes its final correction a fraction of a second before impact. Before we dive in, comment where you are watching from and click subscribe. The B-2 Spirit entered service in 1997 as the product of one of the most expensive and secretive weapons development programs in American history. Each aircraft cost approximately $2 billion to produce at the time of manufacture. A figure that reflects not just the airframe and engines, but the decades of classified research required to develop the radar-absorbent surface materials, the flying wing aerodynamic configuration, and the flight control software sophisticated enough to keep an inherently unstable aircraft controllable at all altitudes and flight regimes. The flying wing design, which eliminates all vertical tail surfaces to minimize radar cross-section, cannot be flown by a human pilot alone. The aerodynamic instability is managed entirely by computers making corrections faster than human reflexes can operate. Without those systems, the aircraft departs controlled flight in seconds. 21 were built across the production run. 20 remain in active service. There is no production line standing by to replace them, no stored components, no restart capability that could be activated within any operationally relevant time frame. Every aircraft that exists is functionally irreplaceable, which means every maintenance decision made on the flight line at Whiteman Air Force Base carries a weight that simply does not apply to any other aircraft in the American inventory. There is no spare. When maintainers talk about getting things right on the B-2, they are not speaking in the abstract. They are talking about preserving 20 assets that represent the irreplaceable leading edge of American strategic air power. The mission begins not at the aircraft, but inside the 509th Munitions Squadron's weapons assembly facility, and the first thing to understand about this building is that it is not a warehouse. It is a precision manufacturing environment. The temperature is held at exactly 68 degrees Fahrenheit, not for the comfort of the technicians working inside, for the ring laser gyroscopes inside the guidance kits being assembled on the workbenches. A ring laser gyro works by firing 2 laser beams in opposite directions around a closed optical path and measuring the interference pattern between them. Temperature variations of even a few degrees cause the optical path to expand or contract, introducing drift errors into the navigation solution. In a weapon system where the entire point is to arrive within meters of a specific coordinate, drift is not acceptable. The climate control is not a comfort feature. It is a precision requirement. Technicians begin by attaching the MAU-169 guidance section to the front of each weapon. Inside this guidance kit sits a GPS antenna, compact enough to fit in the palm of a hand, paired with an inertial measurement unit containing accelerometers capable of detecting movement smaller than the width of a human hair. The control module receives targeting data from the aircraft and translates it into commands for the guidance fins. But the component that receives the most careful attention at this stage is the umbilical connector, the physical and electrical interface through which the B-2 communicates with the weapon while it is still inside the aircraft. Without this connection functioning perfectly, the bomb cannot receive targeting data, cannot be verified as operational, and cannot be trusted. It becomes a gravity bomb with expensive hardware attached. Technicians use calibrated torque wrenches to attach the guidance section because the acceptable range between too loose, which allows vibration-induced failure, and too tight, which cracks the housing, is measured in foot-pounds. There is no judgment call. There is a number, and the number has to be right. The tail kit goes on next. Each fin in the tail assembly is independently controlled by its own electric motor, capable of adjusting its position in increments of 1/10 of a degree. After assembly, technicians run every actuator through a full programmed movement sequence. A fin that binds for half a second during flight translates to a miss distance of 100 feet. The completed weapon is then weighed, not estimated, not approximated. Weighed on calibrated scales because the B-2's ballistic computer uses exact mass figures to calculate release timing and predicted impact point. A 5-pound discrepancy changes the math. Throughout all of this, one principle governs every step of the process. The weapon is completely safe. The fuse is unpowered. The guidance system is in test mode. The thermal battery that powers the fuse will not activate until it experiences the G-forces of being ejected from an aircraft at altitude. Until that moment, the weapon is, in the technician's phrase, a sophisticated lawn dart. Once each weapon passes inspection, it is logged in the weapons database and loaded onto climate-controlled transport trailers. Now, because even a short transit across a winter tarmac can affect the laser gyros, the weapons are ready. The aircraft is not. Out on the flight line, the maintainers of the 393rd Bomb Squadron face a problem that has no equivalent in conventional aviation. The B-2's stealth is not a feature of its shape alone. It is the product of a surface coating that has to be electromagnetically perfect, and perfect is not a figure of speech. The B-2's skin is covered in radar-absorbent material. He has a compound containing microscopic iron spheres that vibrate when struck by radar energy, converting it into heat rather than reflecting it back toward the source. This is how the aircraft disappears from radar screens. But the material that makes this possible is fragile. It has roughly the durability of blackboard chalk. Bird strikes damage it. Hail damages it. Heavy rain at high speed damages it. And damage means radar reflection, which means visibility. Ice, which means the entire premise of the mission is compromised. Before fuel, before weapons, before anyone considers an engine start, the low observable technicians conduct a full surface inspection of every inch of the aircraft. The leading edges receive the most rigorous examination because this is where radar waves first contact the airframe. The engine inlets are critical. Any surface imperfection in the inlet creates what engineers call a radar scatterer, essentially a point on the aircraft that broadcasts its position to adversary radar. The panel seams where separate sections of the airframe meet are filled with conductive tape that must lie perfectly flush. A gap the width of a credit card at a panel seam is enough to increase the aircraft's radar cross-section to a detectable level. When damage is found, and it is always found, the repair process is closer to precision fabrication than conventional aircraft maintenance. The damaged area is sanded with calibrated tools. Too aggressive and you create additional radar reflection. Too light and the repair compound will not adhere properly. The replacement radar-absorbent compound has a working time measured in minutes. It must cure at a specific temperature within a narrow range, because too warm and it bubbles, too cool and it fails to bond to the substrate. Once cured, technicians sand the surface flush using tools that remove material in thousandths of an inch. The finished repair surface cannot vary by more than the thickness of a few sheets of paper across any 12-inch span. This is not painting an aircraft, it is sculpting one, and it has to be done correctly every single time before a mission begins. While the stealth technicians work the skin, other maintainers inspect the mechanical systems. The B-2's hydraulics operate at pressures capable of cutting through steel. 4 separate hydraulic systems provide redundancy deep enough to absorb multiple failures while the aircraft continues to function. The flight control actuators are inspected for any hesitation or sluggishness because on an aircraft with no vertical tail surfaces, every single control surface is load-bearing in the aerodynamic sense. There is no backup rudder. There is no conventional stabilizer. If a control surface on the B-2 fails, it is a serious event by definition. Landing gear, brakes, high tires, environmental systems, electrical buses, bomb release mechanisms. All of it is inspected against a checklist with no optional items. If any system fails its check, weapons loading stops. The aircraft goes back to maintenance. The weapon waits. Once the aircraft is certified, weapons loaders position the JDAMs beneath the weapons bay on hydraulic lifts. The B-2 carries nothing externally. There are no wing pylons, no external hardpoints. And everything goes inside the weapons bays or the mission does not happen. Inside each bay is the rotary launcher, a mechanism that functions on the principle of a revolver cylinder scaled to hold 8 2,000-pound weapons. The entire assembly can rotate 360 degrees in under 3 seconds, which sounds simple until you register that it is spinning 8 tons of high explosive fast enough to induce measurable movement in the aircraft frame. The suspension hooks holding each weapon are rated to 14,000 pounds for a 2,000-pound bomb. That margin exists because a 2G combat maneuver doubles the effective weight of the payload. Turbulence adds more. The engineering conservatism is not excessive, it is correct. The interface between the weapon and the launcher has to be exact. A misalignment equivalent to the width of a penny prevents the JDAM from receiving power and data through its umbilical. Without that connection, the bomb has no targeting information. It falls as a ballistic object and misses by potentially miles. Targeting coordinates are not loaded into the weapon on the ground. The weapon does not know its destination until seconds before release. This serves two purposes: security, obviously, but more importantly, it allows targets to be changed in flight, in real time, in response to battlefield developments that did not exist when the aircraft took off. A target that was valid at takeoff may have moved. A higher priority target may have emerged. The mission computer holds those options until the last possible moment. At the Aircrew Flight Equipment Shop, specialists prepare the gear, keeping the 2 pilots alive at altitude. The B-2's operational ceiling is classified, but it is high enough that a depressurization event is not a discomfort. It is fatal without immediate oxygen access. Pilots wear pressure suits, not simply oxygen masks. Each mask is tested on pressure rigs, simulating high-altitude breathing conditions, including the physical sensation of breathing against positive pressure when G-forces are present. The helmet, which costs more than most residential properties, contains heads-up display integration, night vision compatibility, and a visor that can transition from fully transparent to completely opaque in milliseconds. The design requirement for that transition speed comes from the B-2's nuclear delivery mission. The visor has to protect the crew's eyes from the initial light output of a nuclear detonation before the optic nerve can register it. The anti-G suit receives individual attention for each pilot because fit is performance. Bladder pressures that work for a 6'2" pilot will impair breathing in a 5'8" pilot. On a mission that can last 40 hours with aerial refueling, the physiological fit of the survival equipment is not a comfort consideration. It is a direct operational variable. Hotpit refueling is one of the most dangerous maintenance evolutions in the United States Air Force, and it exists because operational necessity sometimes does not allow for the hours-long shutdown and restart cycle a conventional refueling requires. When a rapid turnaround is ordered, the engines stay running at idle throughout the fuel load. E4 General Electric F118 turbofans at idle generate exhaust temperatures high enough to melt aluminum and kill anyone who walks into the plume without protection. Fuel crews approach in silver proximity suits designed for short-duration exposure to extreme radiant heat. They carry fire suppression bottles rated to project foam 30 feet, because in a fuel emergency near running engines, those 30 feet of standoff distance are the difference between containment and catastrophe. Before anything connects to the aircraft, the grounding cable goes on. This step is non-negotiable and non-deferrable. A B-2 returning from altitude carries thousands of volts of accumulated static charge, an inevitable product of moving through dry air at high speed for extended periods. A single ungrounded spark in the presence of JP-8 vapor does not produce a fire. It produces an explosion. The grounding cable clamps to a specific bare metal point on the landing gear strut before any fuel hose gets near the aircraft. Fuel then flows at 600 gallons per minute through high-capacity single-point refueling connections, loading 167,000 pounds of JP-8 in under 30 minutes. The quantity matters. The distribution matters equally. On a flying wing with no horizontal tail, the balance of fuel mass across the internal tank system is one of the primary mechanisms by which the aircraft's center of gravity is managed. Load too much weight forward and the aircraft is nose-heavy. Too far aft and it becomes dynamically unstable in ways the flight computers cannot fully compensate for. Ground crews monitor flow rate, temperature, pressure, and tank fill levels simultaneously throughout the process. The noise from 4 engines at idle is comprehensive enough that hand signals are the only reliable communication on the flight line. Rotation speed arrives fast on a max weight takeoff. Once the throttles advance past a certain point and the aircraft reaches that speed, the mission is happening. 4 engines producing 69,200 pounds of combined thrust fight 336,500 pounds of fully loaded aircraft down the runway. The nose wheel lifts. Then the wing, reluctantly and with the mechanical deliberateness of something very large doing something it requires a great deal of energy to do, generates enough lift to break from the surface. At cruise altitude, the flight control computers make 1,000 adjustments per second to keep a tailless aircraft stable in air that thin. Without those computers, the B-2 would depart controlled flight within seconds. It is not a forgiving aerodynamic design. It is a design that trades inherent stability for stealth geometry and relies entirely on software to make it flyable. As the aircraft approaches the target area, the weapons bay doors remain closed. Opening them early would generate a radar return visible to every air defense system within range. The doors open for exactly as long as necessary, and no longer. The rotary launcher positions the selected weapon. The umbilical connects the mission computer to the JDAM and begins flooding it with data. GPS coordinates to 10 decimal places, wind speed and direction at multiple altitudes, barometric pressure, time to impact, planned angle of attack. The weapon's internal computer processes this in milliseconds, runs diagnostic checks on every subsystem, confirms fin function, GPS acquisition, inertial navigation alignment, battery readiness. Everything in the space between heartbeats. The suspension hooks release. Pneumatic ejectors push the bomb clear of the bay at 4 feet per second. The instant the umbilical connection breaks, the weapon becomes independent. The thermal battery ignites. The fuse begins its arming sequence, sensing the required G-forces, counting the required time delay before it will arm to detonate. The fins deploy. The GPS receiver acquires satellites, 4, then 6, then 8, and the additional satellites tightening the position solution with each one acquired. The mission computer calculates not a straight-line descent, but a precise curve accounting for wind, air density, and the Earth's rotation. 2 seconds after release, the fins make their first correction. A slight bank compensating for the crosswind, the B-2's sensors measured before release. If GPS jamming degrades the signal, the inertial system continues autonomously. Less accurate, 30 meters instead of 10, but functional. In the final 10 seconds of flight, the fins may make hundreds of small adjustments, each one smaller and more precise than the last. The radar altimeter activates in the terminal phase, providing exact height above the surface. The mission computer calculates time to impact with the precision that the entire preceding process. The climate-controlled assembly facility, the torqued connections, the sanded surface repairs, the calibrated fuel loads, the 40-hour crew endurance, and the 1,000 corrections per second flight computers was designed to produce. One final adjustment, a movement of feet in the last fraction of a second, and then impact within meters of a coordinate that was sitting in a computer at Whiteman Air Force Base before the aircraft ever left the ground.